All right, guys, so we're still talking about thermochemistry, and we have three main concepts when we talk about thermochemistry. We have the one that we've talked about a lot in class, and that's enthalpy. And we remember that enthalpy is that energy that's released or absorbed in a reaction, and that's usually in the form of heat. And so we talk about having exothermic reactions and endothermic reactions, and we remember that exo means that it's going out, meaning that the system is losing energy, and endo meaning that it's going in, which means that the system is gaining energy. So in an exothermic reaction, the reaction is generating heat and losing energy. And in an endothermic reaction, the system is absorbing energy from outside. And an exothermic reaction feels hot, and an endothermic reaction feels cold. Okay, so then we have this new concept called entropy, and you guys did an exercise on this last week, but we're going to talk about this one in some more detail today. So entropy is really just a measurement of the disorder in a system, okay? And your book defines entropy as the number of microstates possible, which seems a little bit crazy to try and think about. So the easiest way to think about entropy is to recognize that if you're trying to keep track of a single molecule or a single atom, the harder it is to keep track of that single molecule or atom, the higher the entropy is. So that means that in the solid state, our molecules aren't moving around very much. They're pretty easy to keep track of. They don't have a lot of disorder, so they have a pretty low entropy. But when we move to a liquid state, our molecules or particles start to move around more. They have more entropy. And if we have that same molecule in a solution, now it's moving around even more, and it's even harder to keep track of, and it's mixed up with the other molecules of the solution. And finally, of course, if we move into a gas state, then we have really high entropy because it's really hard to keep track of the molecules. And then our final concept is free energy. And free energy is that total interchange that the system affects. Okay, and when I say effects, I mean that whatever happens inside the system affects everything outside of the system. And remember, the system is the thing that we're focused on in thermochemistry, and the surroundings are what's around it. And then we talk about the universe being the system and the surroundings. And so we're going to talk about how we can use free energy, the idea of the entire energy change in the whole system, to tell us, not the whole system, the universe, to tell us whether or not a reaction is going to happen. Okay, so we're going to talk about entropy. And the symbol that we use to represent entropy is the capital S. And when you see the capital S with the little degree symbol or the aught, that tells us that that's a standard S, or a standard entropy, meaning that it's occurring at standard temperature and pressure. And standard temperature and pressure in thermodynamics always means 1 atmosphere of pressure and 25 degrees Celsius, or 298 Kelvin. So when we measure entropy, we're measuring the disorder of a system. We're measuring how much the molecules are moving around, how many different possible states they could be in. And that means physical states, not just state as in terms of gas, solid, liquid. So we use the delta S to represent a change in entropy. And so when we talk about entropy in general, we're talking about the entropy of the system. Just as almost everything in thermodynamics, we're always focused on the system. So when it comes to determining the delta S of the system, or the change in entropy of the system, there are really three things we need to focus on. We need to look and see if the state of matter is changing in the reaction, if there are temperature changes, meaning that it's an exothermic or an endothermic reaction. And we also need to think about the number of molecules. Are there more reactants than products, or are there more products than reactants? So we talked a little bit about entropy and states of matter and how that affects it. We know that the faster the molecules are moving, the more disorder there is, which means that if you're in going from reactants to products, you change from a less entropic state, a solid or a liquid, to a more entropic state, a liquid or a gas, then you're going to have an increase in entropy. We also want to think about temperature changes. We know that the more the molecules are moving, then the higher the entropy. So if the temperature goes up, then that also means that entropy is going to increase. And the last thing we need to consider is the number of molecules. If we have more molecules, there's going to be more disorder. So we can talk about number of molecules, or we can talk about number of moles. So let's do a couple of example problems, and let's talk about what's happening to the entropy of this system. So let's take the example of burning carbon. So we have solid carbon, and we're going to add oxygen, and we're going to form carbon dioxide. Now, if we think about our three pieces of entropy, we have some state changes. We're going from one solid and one gas to a gas. So we're going from gas to gas, but we're also going from solid to gas. So there's that piece. This would indicate when we're going from solid to gas that perhaps we have an increase in entropy. We also know that our temperature is going to change. Temperature of our system, this is an exothermic reaction. This is a combustion reaction. And we also need to look at the number of molecules that are present. So we go from having 1 mole of carbon and 1 mole of oxygen to having only 1 mole of carbon dioxide. So even though these other two changes might lead us to believe one thing about the entropy, the fact that the number of molecules is going down is probably going to mean that this system is actually going to have a decrease in entropy. So it's going to have a negative delta S. All right, so let's talk about another example. Okay, so we're going to talk about the reaction that we did in the lab the other day, where we took solid sodium hydroxide and we put it in water, and it dissolved and it dissociated. So now we went from having solid sodium hydroxide to having aqueous sodium hydroxide. Now, you guys know that this was an exothermic reaction because you saw the temperature go up of your surroundings. So we know that these molecules are moving around more. We also went from a solid state to an aqueous state. So we can say that we very definitely have an increase in entropy in this system. Okay, and last example, we are going to talk about a double displacement reaction. So we're going to do this double displacement reaction where we have sodium chloride in solution, and we're going to combine that with silver nitrate, which is also in solution. And now we know from our solubility rules that we're then going to wind up with solid silver chloride and aqueous sodium nitrate. And so we can see that we go from having 4 moles of ions in solution to only having 2 moles of ions in solution and 1 mole of solid sodium chloride. So our number of molecules has gone down and our state has changed to a less entropic system. So we're definitely going to have a decrease in entropy in this system. Okay, so now the question is, what does this have to do with anything? So first we have this idea of enthalpy, and we know that a reaction that releases energy is more likely to happen. But we also know that some endothermic reactions happen. So there must be a thermodynamic reason for those reactions to happen. That's where entropy comes in. So if we have a reaction that requires energy, that energy has to be put in, there has to be a thermodynamic reason for that reaction to happen. And that reason is entropy. If a reaction requires energy, but the entropy increases enough, then that reaction is going to happen. So now our question becomes, how can we predict which reactions will happen and which reactions won't happen? And this is where our second law of thermodynamics comes in. So our second law of thermodynamics says that the entropy of the universe is always increasing. Now remember, the universe is the system and the surroundings. And so the entropy of the universe is always increasing. This means that any action that's taken to offset or decrease the entropy of the universe has consequences somewhere else. So you can tell your parents this is why your room is a mess, because the entropy of the universe is always increasing. And if you try to decrease the entropy of the universe by making your room nice and clean, then that has a cost. And in your case, that cost is a thermodynamic cost. It's an energy cost. You have to put energy in to decrease the entropy. Please don't tell your parents I said that. Okay, so the entropy of the universe is always increasing. So can we use this to figure out which reactions are going to happen? We're setting aside the room cleaning for a moment. Yes is the answer, right? If we can find a way to combine entropy and enthalpy, then we can determine whether a reaction will increase the entropy of the universe, which will then mean that that reaction will happen. So we introduced this concept that we call Gibbs free energy. And Gibbs free energy, you guys will remember from your activity last week, we symbolize with a delta G. And just like heat, we can't measure free energy alone. We can only measure changes in free energy. So Gibbs free energy we can calculate two ways. We can calculate Gibbs free energy by saying that it's equal to the change in enthalpy minus the temperature times the change in entropy. Because we remember that entropy is temperature dependent. And when we put this all together, this is Gibbs free energy. And Gibbs free energy is a way for us to measure the change in entropy of the universe, because it takes into account both the entropy change of the system and the enthalpy change of the system. And remember that if there's an enthalpy change in the system, that's also going to cause an entropy change in the surroundings. So, for a reaction to be spontaneous, that is, for a reaction to happen at a particular temperature, the entropy of the universe has to increase. If the entropy of the universe is increasing, Gibbs free energy is going to be negative. That means that the energy of the system, the overall energy of the system, the Gibbs free energy is going to be negative because the system is losing, the surroundings are gaining. Okay, so we can calculate Gibbs free energy. So we're going to do a practice problem. We're going to talk about the formation of ammonia and hydrogen chloride from ammonium chloride. So in this reaction, ammonium chloride, which is a solid, is going to break apart, and we're going to have ammonia, which is a gas, and hydrogen chloride, which is also a gas. So just looking at this, we can tell already that entropy is going to increase, which means that this piece of our equation is going to have a positive sign. Now I can tell you that the delta H of this system, the change in enthalpy of this system, is negative. It's negative 176, as a matter of fact. And you can see, just from the fact that we have a negative delta H and a positive delta S, that we're going to have a negative minus a positive, which is going to give us a negative. So right off the bat, we already know that this is going to be a spontaneous reaction because delta G is going to be negative. But let's go ahead and fill in our numbers here. So we know that because we can look it up on our tables of thermodynamic values, that the standard change in enthalpy for this reaction is negative 176 kilojoules per mole. And this is happening at standard conditions. So our temperature is going to be 298 Kelvin. And our delta S, again, we've looked this up on a table, is going to be 0.285 kilojoules per mole Kelvin. Okay, so now we have negative 176 minus 298 times 0.285. And so that's going to give us a delta G that's negative 261 kilojoules per mole. So what that means is that for every 1 mole of ammonium chloride that reacts, this system is going to release 261 kilojoules per mole of energy. We can also, because Gibbs free energy, just like enthalpy, is a state function, we can calculate delta G from standard formation energies. So we can use tables of thermodynamic values to do that. So let's do one more quick example like that. Okay, so one more way that we can calculate Gibbs free energy. As I said, because this is a state function, just like enthalpy and entropy, it only matters where you start and where you end. So if we know the standard Gibbs free energy of the products and the reactants, we can use Hess's law. And we can say that the standard Gibbs free energy of the reaction is equal to the standard Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So we're going to use this one as an example. We're going to do a combustion reaction of methane. So we're going to combine methane with oxygen, and we're going to wind up with carbon dioxide and water. So first thing is to find the sum of the standard Gibbs free energy of the products, and we have our products here. So since we have 1 mole of carbon dioxide, we're going to have negative 394.38 kilojoules per mole, plus we have 2 moles of water, so we're going to multiply the standard Gibbs free energy of water by 2. So we're going to have 2 times negative 228.59 kilojoules per mole. And then that's the sum of the Gibbs free energy of the products. And then we're going to subtract the sum of the Gibbs free energy of the reactants. And if we look over here, we can see that the Gibbs free energy of methane is negative 50.84 kilojoules per mole. And the Gibbs free energy of oxygen, because it's an element in its pure elemental state, is going to be 0. So when we sum those up, we wind up with a total of negative 800.72 kilojoules per mole of reaction. And that's how we use Hess's law to find Gibbs free energy.